Now that we've learned about chemically what an acid or a base is, it's time to look at the measurement scale that is used to represent how acidic or basic a substance is, which is what we call the pH scale. So the reason why pH is actually written like this with a lowercase p and uppercase h is that the uppercase h actually directly refers to H plus ions, which, as we know from the acid video, every acid releases when they are dropped into water to ionize. Now the P stands for the word power, which mathematically is the same word as the word exponent. For example, 10 to the exponent 2 can also be phrased as 10 to the power of 2, meaning that power of hydrogen refers to the amount of H plus that exists in solution, meaning that pH looks at the strength of acids and bases framed from the perspective of acids and uses a numerical scale that goes from 0 at the low end to 14 on the high end. Now, if we look first at the low range of pH, which is a pH of 7, which is right in the middle of 0 and 14, and go downward to 0, this is what we define as a low pH, and rather counterintuitively, even though pHs are framed from the perspective of acids, it's actually a low pH that refers to being a substance being more acidic rather than more basic, meaning that a substance produces more H plus when ionized in water and less OH minus. Conversely, if we start at the midpoint 7 and go all the way up to 14, we have a high pH, which indicates that the substance is more basic than acidic, meaning that more OH minus is produced in water and less H plus is. What about the midpoint? What about the pH of 7? Well, a substance that is neither acidic nor basic is defined as being neutral, and this is where the word neutralization in reactions that react an acid with base in order to make water, this is where the word neutralization actually comes from, because pure water, which is a combination of H plus and OH minus that join together, is neither an acid nor a base. And in future grades, you'll actually see that water can function as both depending on the situation. And for that reason, because it is equally likely to be an acid and a base, because it can break apart into H plus and OH minus, this is why we define pH of 7 as the pH of water as being neutral. Now, one of the most misunderstood parts of reading the pH scale is the significance of what the numbers mean, because pH is not a regular numerical scale. It uses a system which is what we call a logarithmic scale. If you have heard of the term a magnitude-based scale, this is another word that is used in place of the mathematical term logarithmic. What this means is that a pH of 1 is not simply one pH value greater than a pH of 0, and a pH of 3 is not simply two pH values greater than a pH of 1. Each pH number is different by a factor of 10 times that adjacent number. For example, we see that pH of 1 is closer to the acidic side than a pH of 2, so we can say that a pH of 1 is 10 times more acidic than a pH of 2, because every time we change from one pH value to the next, we are operating at a factor of 10 times. Conversely, if we want to go to the basic end, we can see that 13 is closer to the basic end than 12 is, so we can say that a pH of 13 is 10 times more basic than a pH of 12. Now, this gets a little bit more complicated when we deal with non-adjacent pH values, but that's why we can do some quick practice here. For example, gastric juices, also called your stomach acid, we can see commonly have a pH of 2, whereas tomato juice, which is also on the acidic end, has a pH of 4. And what we need to do in order to see how much more acidic or basic stomach acid is to tomato juice is to take the greater pH of 4 and subtract 2 from that, the lesser pH, and we end up with 2. Now, we know that each difference in pH corresponds to a magnitude of 10, so if we were to do this, 10 to the exponent 2, well, we know that this is 100. Or if we want to do this the really simple way, here's a pH of 2, that's 10 times, and that's 10 times 10 times. 10 times 10 is 100 if we want to count that way. So based on this, we can say that stomach acid is 100 times more acidic than tomato juice. We could also say that tomato juice is 100 times more basic than stomach acid is, because it's closer to the basic end than stomach acid is, and therefore it would be more basic. If we try another example here, let's actually skip the other acidic example and actually go down to the bottom, let's try C here. So if we check hand soap versus household bleach here, so again, we take the higher pH value, which is a pH of 12 for bleach, and subtract pH of 10 for hand soap, and we get a difference of a magnitude of 2. And if we do this again, 10 to the exponent 2 is 100. So we can see here that hand soap is 100 times, and because hand soap is less close to the basic end than household bleaches, we would say that hand soap is 100 times less basic than household bleaches, because again, its pH is closer to the maximum end of the basic side. Now, for an interesting one, if we compare the most acidic and most basic substances here, household bleach with a pH of 12 and stomach acid with a pH of 2, we see that they're different by a magnitude of 10. And if we wanted to actually find out what this number is, it would be 10 to the exponent 10, which is just 10 with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this number, if you're not familiar with how many zeros this is actually 10 billion. So what this means is that stomach acid is 10 billion times more acidic than household bleaches. And if you want to phrase it the other way, we can say that stomach acid is 10 billion times less basic than household bleaches, and the result would remain true based on how the magnitude system of the pH scale works. Now that you've been introduced to the pH scale and understand how to gauge how much more acidic or more basic a substance is, the remaining 2 videos in this series will go over the naming conventions about how to name binary acids and oxyacids.